So this is Alfonso Berumen. I am a decision sciences faculty at Pepperdine University, and I actually teach in the doctoral program, more specifically quantitative methods for. And what we'll cover today is actually a common mathematical technique that's used in analyzing survey data prior to modeling. So we'll talk about both exploratory factor analysis and confirmatory factor analysis. So I have an example up. So we're going to be using their data as part of the demo from this research study. It's actually based on the Unified Theory of Acceptance and Use of Technology, or UTAUT. So it's actually a well-known model of user acceptance of IT. It's based on elements from several prevailing user acceptance models. You can see that in the abstract. As well in the abstract has been credited with explaining a larger proportion of variance of intention to use and usage behavior than do preceding models. The sample that they have in this research study is based on 722 individuals using desktop computer applications in Saudi Arabia. And they actually looked at this modified version in determining intention to use and usage behavior. They did find that the model explains 39.1% of the intention to use variance and 42.1% of usage variance. So what I want to scroll to is a visual is going to help with this is they have this behavioral intention to use and then use behavior variables. There's these constructs here that we'll look at or evaluate, and the idea is that you would have these constructs such as performance expectancy or effort expectancy, and try to see how those best explain different levels of, say, behavioral intention to use, right? So we have those constructs that we'll take a look at, but we'll see if you kind of bear with me, you'll actually see that all those constructs are measured, right? So they're measured based on survey questions that your respondent would answer. So this is actually on a Likert scale, so you can see the PE, EE, and what items or questions were proposed to these sample respondents. And the idea is, you would basically have several questions associated with each, and the hope is to measure that particular variable. So you can then do your statistical analyses to look at those relationships. So I'm going to actually use R. So R is a common software that's used to do what we're referring to here is factor analysis. Should probably move my face. And the way this works is I have this code here. I have several different libraries that I'm going to use. I'll go ahead and load these. This isn't going to be a live coding session. I have this code kind of pre-populated, and I will share this, but you should be able to plug and play for your own model as you look at applying factor analysis. So this is my folder. So whatever folder you're working out of, you just modify this to wherever your data is stored. So this is where my data is stored, or this folder path is where my data is located. So I'm just going to set that. I'm going to import my data into R, and you can see that data there. So you can see the Likert scale and each of those items. So pretty easy to follow. So the first thing I'll look at is actually correlations, and what you'll see here is that I actually have a kind of pretty version or correlation matrix And let me print that out and run that. And you could see if I open this up, I do actually have some correlation coefficients that are a little bit higher. It's like PE1, PE2, PE3, PE4. All of those are kind of in the higher side. You can kind of see the darker circles that would indicate that. In this setting, it's not necessarily a big concern. These are actually reflective constructs, which means these items are going to be maybe a little bit redundant, right? So in other words, if I take one of these items or questions away, the rest of the items should pretty much take care of that construct or capture it. So I actually expect people's responses to be similar, and I hope actually that they're somewhat correlated when we look at those responses. So you could look at some detail in there and look at each of the individual correlation coefficients. That gives me a pretty good sense of what's going on from a correlation standpoint. Um, but what we'll then do is look at, is it the data we have, is it sufficient to move forward with factor analysis? There's a couple of things that we'll look at. Bartlett's tests in the Bartlett's test, sphericity is what it's called. That's the first. We're first going to look at the creating a matrix that we may need to use later. Um, but let's go ahead and look at the Bartlett's test. And you could actually use either of these processes. You could use the data itself or a correlation matrix. I'm going to go ahead and run that, and we'll take a look. And you can see the chi-square p-value. So p-value, we're actually rejecting the null that this is a identity matrix. And so that's your null hypothesis. We have an identity matrix. Our p-value is very low, right? Less than 0.05, basically zero. So that means we can reject that null. And that would suggest to us that we can actually move forward with factor analysis. So in addition, we have this KMO that we'll look at. So the KMO, go ahead and run that. And when you think about the KMO, it's a measure that quantifies how suitable our data is for factor analysis by looking at simple correlations to partial correlations. So it's going to range from 0 to 1. And greater than equal to 0.9, that would be excellent for us. 0.8 to 0.89, pretty good. And then we're going to fall into the middle with the 0.7 to 0.79. So we're actually pretty good here. That would suggest to us that we can move forward with our factor analysis. All right, so anti-image matrix we'll take a look at as well. So we're actually looking at the off diagonals, and we're looking for larger values. So I'm going to run this block here, and then also flag those larger values and print those results. So you can see here when I ran that, I do have some values, off diagonal values that are larger. You can kind of see here, larger an absolute value of 0.2. So that would be going too far. You can actually see that there are some that are actually pretty high. Let's look at actually the PE because I talked about that one later or earlier. The PE3, PE2, right? You see those are an absolute value, or it's an absolute value of 0.52, right? Which is much larger than 0.2. That actually means that there's kind of this overlap within PE, right? So there's kind of this overlap. Doesn't necessarily suggest to us that there's a something horribly wrong, right? But we might actually kind of look at those questions and may lead to kind of maybe dropping or rewarding some of those questions. But there is kind of this overlap within PE, and there are some in some of the other constructs as well. So you can look at that in detail, relate to your own study, but we're going to move forward. And the last thing we'll look at is the determinant of the correlation matrix. And that is really, really small. So the rule of thumb, though, is that if that's over point, and there's four zeros, so 0, 0, 0, 0, 1, we should be okay, right? So we're going to be okay here with the determinant. This is actually scientific notation, so you can actually go kind of 5 to the left here. So, if I were kind of printing this out, actually, let me um, see if it'll print here. It still shows up as scientific notation, but I'll actually show you that that actually translates to this, right? It'll translate to that. Um, so we're good there. So no multiclinarity. That's our takeaway from the determinant. So finally, we're going to look at uh, the factor analysis. But before all that, we can kind of summarize all this as bar this test. We're good. KMO, the overall at 0.86 is strong. And then also there are some kind of red flags with the anti-image, but we might review those in a little bit more detail and determine it. No collinearity, so we're good there. So we're going to move on to the factor analysis. So you go forward with the factor analysis. Again, we can kind of save a correlation matrix, and then we can do that. And you have that object there. I might have some redundant correlation matrices. That's okay. Um, and you'll actually use your this eigen function to get what are referred to as eigenvalues. So an eigenvalue is basically the amount of variance in the data that's explained by a factor or component, if you're using the term component. The way to think of the eigenvalue is the higher the eigenvalue, the more important that factor is in explaining patterns in your data. So you can see here, let's actually look at a couple summaries, so sum, cumulative sum, and then we'll look at the proportion as well. So you can see when you look at your eigenvalues, one of the things that's often looked at is you would suggest that in terms of number of factors to use based on this this data, we should stop at 1, right? So anything over 1 is okay. That means we should use a five factor framework. But then we also have the sixth one, right? So it's actually under 1. So what we're basically doing here is with factor analysis, or in this case, starting with exploratory factor analysis, we're trying to say, hey, we don't really have an idea quite yet on what these constructs represent. So I know that's in conflict with what I just showed you because UTAUT, there's very clear constructs, clearly defined constructs. So in theory, it should be clearly cut and defined, right? Um, but you may be in a situation that's different than this, or slightly different than this, that you don't know what those variables or what those variables actually correspond to, right? So you might have a construct like leadership. You ask a bunch of questions. Hopefully, it kind of translates to leadership. But you also might have other questions in there, right? Around maybe I don't know happiness. Well, that's a complex one. But you might have other questions that may be capturing other things. And the idea is hopefully you can kind of clearly define. Okay, there's a construct corresponding to leadership, construct corresponding to happiness. Um, and so on, right? So you have these kind of abstract constructs you're hoping to ask questions around to capture in a survey setting. Okay, so long story short, we're going to move forward and see, okay, well, if this were exploratory, which it's not, right? UTAUT is a sort of highly utilized and highly accepted way of sort of capturing or understanding usage behavior with respect to IT. Um, if I had no idea, what would factor analysis tell me? And this is where exploratory factor analysis would come in, is we're basically exploring and testing to see, okay, what do these items, do they measure what I intended to measure? So in this case, we'll actually see that it actually suggests to us, based on that eigenvalue cutoff, that we should actually stop at 5, right? We should stop at 5. But we actually know that, in fact, there's 6 different factors in there, right? So I also might look at this scree plot, what's referred to as a scree plot, and I have a little line there that is drawn at 1, and you can see there that this 6th one, I know it's just below 1. So I actually have a pretty good justification to use 6. And in fact, it actually is backed up with my theoretical model. But the cumulative variance explained for the first 6 factors is about 59%. And I saw that. So you can kind of see that when you look at the percentage, right? So you can kind of go across and kind of see, okay, 1, 2, 3, 4, 5. So you can see that, in fact, we have 1 factor, 2 factor, 3 factors, 4, and then 5. So we're actually going over. I want to be clear on that. We're actually going over 59% when we get to 6, right? So 1, 2, 3, 4, 5, and then 6. So in fact, actually, we're getting over 69, 69%, right? So pretty good, or sort of feeling pretty good about that. But when we kind of think about this, is when you look at your scree plot, sure, you can sort of see where that bend occurs. And actually open this up again. Where'd it go? There you go. Yeah, so you can see where that bend sort of bend occurs. Um, that's another way that this scree plot is actually used, right? So where does this actual bend occur? And the idea is we're not really getting much value after going further, right? So after going further from that bend, we're really not getting much value because we've already explained a large proportion of the variance in the data, right? So this is how we can interpret that scree plot and use that information for decision making on how many factors we should actually use, or how many factors we actually have. So though that what's referred to that one eigenvalue of 1 cutoff, it's actually called the Kaiser's criterion. And so despite that criterion recommending maybe 5, right? So recommending 5 based on this, um, we could actually retain 6. And the 2 main reasons: it's theory driven, right? Theory driven based on the UTAUT model, and a little power adjustment there. So it's actually theory driven, based on the UTA framework, which consists of 6 constructs, and then also the statistical indicators support a 6-factor solution, right? So the 6-factor actually has a eigenvalue that's pretty close to 1, um, and adds a little bit of variance explained that's meaningful enough. Let's just put it that way, right? So we actually have a justification to use, as opposed to 5, 6, 6 for that factor analysis. So that step was actually determining how many factors should we use, and in fact, we're actually going to apply 6. So both of these are proper factor analyses. So it's not PCA, which is often confused with factor analysis. So this is using maximum likelihood factor analysis, and you can kind of take a look at that output. And what we're mostly concerned about is these loadings, right? So these actually help with interpretability and understanding what each of these factors represents, right? So you can think of the loading as kind of this correlation related to that factor. So you would interpret that in that way, right? So you can kind of see factor 1 loaded, so loading from subjective norm, right? So you see subjective norm, high values there, right? So this first factor actually would likely capture, or you would likely translate it to that it captures this construct subjective norm, right? So you can make similar inferences from some of the other factors, right? You're looking at, okay, well, these items, which ones have high loadings to that factor, so then you can qualify, okay, that mostly represents that particular construct. Okay, so that's one version. What will also help maybe was with this is there's another type referred to as principal axis factoring. Again, these are not PCA. And we're also going to rotate with Verimax. So we're going to apply orthogonal rotation. That is often common for interpretation purposes. There are different rotation types that I'm not going to get into. We could get into a deep discussion on that. But you can see there are actually a lot of variations of factor analysis out there. And so we're actually going to choose principal axis factoring and kind of take a look here. So when we think about here, we have the loadings, right? So you have the loadings. So I just extracted the loadings. We could actually look at all the output, and if I scroll here, so you can see these standardized loadings. There's a number of different elements that we could kind of look at and pick at. But when we kind of jump to the yeah, so you actually have standardized loadings here, and you can kind of see what the different values are for the standardized loadings. Let's kind of look at the first. If you look at this first factor, right? This column here, you can kind of see basically that this first one largely measures the effort expectancy, right? You see these high loading values here. You also have the second one, so PA4. You can see that there largely is performance expectancy, right? So you can kind of see those. You kind of look across and look at PA4. So basically making kind of similar assessments or similar statements around the factor analysis and what each of those kind of represent, right? So The other thing we can also look at, and there are elements you can look at in more depth, um, but one of the things we can also look at is also just creating a heat map to understand this a little bit better. And so let me actually go ahead and kind of create that guy. And if I go ahead and run this and take a look at that heat map, this also tells us a similar story, right? What's the kind of separation for each, and what these different factors represent? There are some, kind of maybe questions for us, right, in terms of what that factor actually represents when you look at some of their factors. But you can kind of see where we kind of looked at it was the first one and the second one kind of more clear cut, and also the third one, which is PA2, it's pretty clear cut as well. So let's keep going. The last thing we're going to look at is the residuals. So if we look at those residual stats, and you can see that block there. Yeah, for the residuals, we actually have a root mean squared residual of 0.1 or 0.018. So well below a good common threshold of 0.05, indicating a good fit or excellent fit. Three out of the 210 indicate very, for us, there are very few large residuals, right? So we don't want a lot of, in absolute value, the residuals to be over 0.05, so we're just counting those up. So we don't have a ton of those. We actually have a very small amount, which actually corresponds to about 1.4%, right? You can see that at the bottom there. General cutoff is 5%, so we're well below 5%. So we feel pretty good about that as well. So the what the takeaway of what this tells us is we're still pretty good with that six factor model. So this would kind of further validate keeping six factors despite that sort of five cutoff we talked about earlier. All right. So what we'll go ahead and transition to after this figure recording is actually the second part is looking at reliability, right? So once we've already had our EFA done, and we're now accepting, okay, well that we feel pretty good about six. Let's actually see in terms of the reliability what that looks like. So that'd be the next kind of next step or next part of this tutorial.